Welcome back after lunch. And we're going to have Pedro Montero from the Universidade Santa Maria in Valparaíso. And he's going to talk on the unipotent group structures on quintic del pairs of varieties. Thank you, Pedro.
Thank you, Eduardo, for the nice introduction. Thank you all for being here, the organizers. I'm very happy to be here, actually. My first time in IMPA was 10 years ago for the summer program, so I'm super happy to be here, actually, as a speaker of this very nice conference. So I will speak about the joint work with Adrián Duboulot and Takashi Kishimoto about quintic del pezzo varieties. So let me start with a motivation, a very old problem by Hirzebruch, stating the following. So suppose you have a fixed dimension, n, and you want to classify pairs x delta such that x is a smooth projective manifold of dimension n, delta is a divisor reduced, such that the complementary of this divisor is the affine space. So you have like maybe a bunch of irreducible components of your divisor delta, and you have an open subset U. Oh, sorry. Oh, okay. And you have an open subset U, which is isomorphic to the affine space of the corresponding dimension, right? Of course, if let's say if you're in dimension 2 or higher, you can pick up any point on the boundary, you can blow up, and you can get a new example. So some sort of minimality assumption is to impose that the Picard number of the second Betti number is 1. So in such a way, you have some, I don't know, you avoid this kind of a blow up, new examples by blow up. So I don't know, using the technology, the language of cones of divisor, you can easily prove that in this case, X has to be a Fano manifold. But at that time, even without this technology, Kodaira also realized that. So X, in this case, is Fano. And moreover, the anticanonical divisor has to be a multiple of this boundary, okay? So a very simple and nice example is the projective space, right? You take a hyperplane, you remove it, and you get the affine space, right? Let me recall you some very classical result by Kobayashi and Oshiai, which is also related with this, this identity here. If you have a Fano variety, the Fano index measures, essentially, how ample is the anticanonical divisor. This number is in between, so the anticanonical divisor can be written as the Fano index times some ample divisor. This number, let's say by Riemann-Roch, is in between 1 and the dimension plus 1. And this classical and very important result tells you that if the index is n plus 1, then it has to be the projective space. If the Fano index is n, then it has to be a quadric, a smooth quadric inside Pn plus 1. And actually, we have a classification of Fano variety with a high index. Say, if the index is n minus 1, then these are so-called del pezzo varieties. I will speak about this again later. And if the Fano index is n minus 2, then these are Fano Mukai varieties. So we have a classification when the Fano index is high. So going back to the problem of Hirzebruch, of course, in the small dimension, you can say essentially everything. For curves, since it's a rational curve, a Fano curve has to be P1, and the boundary divisor is just a point. Again, by classification of surfaces, by Enriquez Kodaira classification, essentially, you can easily prove that the only example in dimension 2 is the projective space, removing a line. And in dimension 3 and higher, the problem gets, more interesting. There are actually many examples. Well, essentially 4, but there are non-trivial examples. This was done by many authors, but this was finished by Furushima. And so we have 4 varieties. So here you have, of course, the projective space, and you remove a plane this time. You get the affine space. You can also pick a smooth quadric and consider this cone. So there's a cone over a conic on P2. This is a divisor. You remove it, and then you get the affine space. And there are two interesting examples in dimension 3, B5 and B22. And actually, this is interesting because you have two different boundaries, actually, surfaces in this case. One of these surfaces is normal, and the other one is non-normal. So there are actually two different compactifications of the affine space. Okay. So this B5 is in green because this will be important for the talk. So let me recall you what is the threefold B5. So it's the following. You consider the Grassmannian of two-dimensional linear subspaces of C5. So if you want projective lines on P4, and you take the Plucker embedding onto P9. Okay, this is a 6-dimensional variety. And you take here a smooth hyperplane section. You get a 5-fold. Let's call it Z. Then you take another hyperplane section. You get a 4-fold. Let's call it W. And then you take another hyperplane section. You get a 3-fold, which is V5. If you want, you can take another one. You get the quintegral Petzl surface. But let's stop there. So each of these varieties are also different because they have the different Fano index, as you may see over here. And a very nice observation is that by a recent result by Kuznetsov, Prokhorov, and Shramov, these are the only Fano trifolds of Picard number 1 whose automorphism group is infinite. So they have many symmetries. There are also, I have to say that in dimension 4 or higher, this problem is completely open, essentially, the classification. But there are some partial results by Prokhorov, Seidenberg, and all these examples have infinite automorphism group. So it was a nice idea to try to look at, some additional structure on this kind of varieties. And maybe we can try to say something if, I don't know, the automorphism group is infinite or something like that. So this motivates the following definition. If we have a nice algebraic group, so let's say linear, I don't know, we don't need reductive, but just linear, say, and you have a normal projective variety, then you can consider a nice action. What is a nice action? So you have an action of your algebraic group, and you pick a general point, and the orbit is dense, and the stabilizer is trivial. So in that case, what happens here is that your open set is isomorphic to your group. So it's essentially an equivalent compactification of your group. And so, of course, there are very nice examples of this situation. Maybe the most famous one is our toric varieties, where the group is the algebraic torus, right? But here we will be interested in another kind of varieties, additive varieties. So the group will be GAN. So essentially, it's just the affine space, but with the sum. So it's the vector group also. It's also called the vector group. Well, as you may know, for toric varieties, we have a lot of geometry. We have a lot of combinatorics. Everything can be translated into fans, polytopes, etc. Sadly, for additive varieties, we don't have that kind of situation. Even worse, for toric varieties, as you may know, toric varieties are essentially toric in a unique way. Up to change of coordinates, the action is essentially the same. But here, in the case of additive structures, we can have different kind of ways to being additive. So this story started actually by a very nice work by Hassett and Schinkel. It's a very nice correspondence between additive structures on the projective space and some commutative algebra stuff. So as the conference, commutative algebra, algebraic geometry. So rather than explaining the whole correspondence, let me give you an example, a concrete example for P2. So you have to consider commutative local alt in C algebras of dimension n+1. Okay, so it's a ring, and as a vector space, it's of dimension n+1. So let's say 3. So you can projectivize this vector space, and you get P2, right? But it's interesting to not forget that this is a ring, and to consider, say, the generators of the maximal ideal, and then you can cook up a linear combination of one generator plus the other one, so A1x plus A2y. Then you take the exponential. A priori, this exponential is an infinite series, but since you're on a local ring, this has to end at some point. So you have some finite sum, right? So it's a finite sum, because the ring is Artinian. And almost by definition, it's commutative. So you have because of the properties of the exponential, right? So you have a GA2 action on the projectivization of this three-dimensional vector space, which is an algebra. These two algebras are examples of these nice algebras. The ring of polynomials on x and y quotiented by this ideal. They're actually different because, I don't know, you can see, I don't know, you can check the Hilbert-Samuel series if you want. They're actually different. And the induced additive action, additive structures are actually different as well. For instance, the first one, which is the naive one, you can see it's essentially the most naive additive action that you can think of. If you fix, for instance, the x2 equals to 1, this is just adding a2 on the first coordinate, a1 on the second coordinate. So it's the most naive action. The second one is less naive, and the orbits are very different. For instance, in the first one, the line x2 equals to 0. Every single point on this line is an orbit, it's a fixed point. But for the second action, this line is fixed, but there is a non-trivial action in, there is only one fixed point. So in the first case, you have infinitely many orbits, so each point of this line. But for the second one, you have 3 orbits. So there are actually different ways to be additive. And OK, you can, well, this is a very nice example. And if you think about it for a second, I mean, you are on P2, right? You have 3 by 3 matrices that commute. So this is a very, very classical thing from commutative algebra, yeah, right? Commuting matrices. And there is a classical result by Suprunenko that can be translated, of course, it wasn't stated in this way, but can be translated by saying that if you look at the number of, non-isomorphic ways to be additive for the projective space, then for P1, you only have one way to be additive. For P2, you have 2 ways, those that I showed you. For P3, you have 4 ways. For P4, 9. For P5, 25. And from P6 and higher, there are infinitely many ways to be additive. So it's very different from the toric situation. This will appear again in a few minutes. OK, so using this, Hassett and Schinkel considered the following problem. So you have the very classical problem by Hirzebruch, classifying these pairs, x delta, say, with Picard rank 1. So x has to be Fano. If you impose, I mean, Furushima and many other people work on this problem, but if you impose that this has to be an equivariant compactification of the affine space, then there are only 2 options. It has to be P3 and the quadric. So you can rule out this V5 and V22. And let me just show you a very, very, very brief sketch of proof, because it's interesting for the rest of the talk. The main ingredients that they used are the following. So if you have an additive variety, so an equivariant compactification of this algebraic group of Picard rank R. So this translates geometrically, saying that you have R irreducible components here. So first of all, well, you have this boundary. And the anti-canonical divisor for these Fano varieties is a sum, as in the Picard rank 1, and as in this case, we had that this was some multiple of delta. Here you also have the same, but which is more interesting, I would say, is that the coefficients has to be 2 or higher. This is different as well from the case of toric varieties, where all the coefficients are 1. So it's somehow is more positive. The anti-canonical bundle is, line bundle is more positive in this case. So in particular, if the Picard rank is 1, then the Fano index is at least 2. And this can, I mean, from this you can rule out the B22, for free. So you're reduced to exclude this case, B5. And I already told you what is B5. And the contradictions, there are many ways to argue at this point, but the original argument was to consider a Sarkisov link. I won't explain what a Sarkisov link is, but it's a nice birational map onto the smooth three-dimensional quadric. And on the three-dimensional quadric, you can do everything in a very explicit way. So you can actually describe the action in coordinates, and you can do the, the reverse way to the inverse Sarkisov link, and get a contradiction. Okay, I won't enter into the details because I will do essentially something similar in a few minutes. Another way to, by the way, to prove this in a very short, with a very short argument, is that it can be proven that the automorphism group of this threefold here is PGL2. So it's a three-dimensional algebraic group connected, right? So there's not enough, which is not commutative, so there's not enough space to have a GA3 inside, which is also three-dimensional and commutative. So that's an easy way to argue. But this geometric way will be useful for us in a minute. OK, so let me give you some results now. The title of the talk involves Del Pezzo varieties. As I already told you what is a Del Pezzo variety, are Fano varieties of dimension n and Fano index n-1. So these were studied by Fujita, and they were classified according to their degree. So the degree of this variety will be this guy, sorry. This will be the degree. And in a very, for Del Pezzo surfaces, you know that the degree of the Del Pezzo surfaces is 1 up to 8. These surfaces are P2, P1 cross P1, and some blow-ups of P2 at some number of general points, at most 8. So you can check that these are the possible degrees for surfaces, and for higher dimensional analogs of this kind of varieties, the same is true. And we proved the following theorem with Bahua Fu a few years ago. Is the following. If you take smooth Del Pezzo varieties, and you ask for this question, whether this variety is additive or not, then we have the following. If the Picard rank is 1, then it has to be a quintic Del Pezzo variety, and the dimension has to be 4, 5, or 6. So let me just use some color here. These are additive, okay? And this one is not, as I already told you. And if the Picard rank is 2 or higher, then it's also very explicit. It's a product of P2, some blow up, some product of P1. It's very explicit. Even better, in the second case, in this, Here we can, since we're essentially in the projective space or blow-ups, we can essentially do everything in coordinates thanks to the work of Hassett and Schinkel. They already did the work for us. But for the first case, for the Picard rank 1, for the BTU2 of x equal to 1, there is a problem that we essentially were at the end of the minimal model program. So we cannot use essentially, we cannot contract anything. We have to look at Sarkisov links. That's what we did actually now. But at that point, we didn't use this technique. We used another technique, which is called the variety of minimal rational tangents. So these varieties are full of rational curves because you have a big AN inside. And you can describe this, some family, some sort of modulus space of rational curves inside. And we use this to prove this theorem. I won't enter into the details, but I wanted to tell you that the problem is that this first result on the BT2 equals to 1 case is very existential. We don't have anything which is anything explicit. We only know that there is a way to make this variety additive. So this is not a very good answer from the point of view of the Hirzebruch problem. So we don't know what is the boundary at this, using this result. And also, as we already saw this morning, it's very important from the point of view of the minimal model program to consider singular varieties. So unfortunately, this BMRT stuff, I mean, it's not yet, how to say, developed in the singular case. And another thing is that what if the ground field is not algebraically closed? To be completely honest, I mean, you can argue here that this is very interesting from number theory point of view. I don't know if you want to treat the rational numbers of the real numbers. But to be completely honest, we wanted to look at the fibrations, right? To fibrations of Fano varieties, so you have to look at the generic fiber. So it's a Fano variety defined over this function field. Even over the complex number, this is not algebraically closed. So you have to, I mean, try to say something if you want. And this is our main theorem. With Adriana and with Takashi, we proved that if you have you start with this Grassmannian, six-dimensional Grassmannian, you take a smooth, you take a linear section. If this section is smooth, then there is a unique way to be additive, as long as you are in the right dimension, right? 4, 5, or 6. And moreover, we can describe this boundary divisor. So essentially, this is very nice because it's the original question by Hirzebruch. But not only, since we use now some explicit circuits of limits, we can actually treat some singular cases. For instance, if X is a terminal threefold, I won't explain what terminal means, but it's a very nice kind of singularities. For instance, the singularities are only isolated points. Then you can prove that there is an additive structure if and only if you have very few singularities, actually 3 nodes as singularities. And you can also treat the case of surfaces, so quintic del pezzo surfaces. In the smooth case, there's no hope, because if you take a quintic del pezzo surface, the automorphism group is finite. However, if you allow some mild singularities, actually canonical singularities, which are the mildest one, if you want, then you have a structure if and only if there is a very precise description of the singularities. 1 point of type A4, 1 point of type A3, and depending on which kind of singularity, then you may have 2 additive structures or maybe only 1. So this is the whole picture. And what I'm not telling you, and actually which is I think most interesting part, is that we actually don't need the field to be of algebraically closed. Because essentially, I will explain you, but essentially because everything is very, tautological, canonical. Essentially, we are dealing with Grassmannian, so we can do it over any field. And at the end, I will tell you an application of this to forms of these varieties. So as you may know, if you are in a non-algebraically closed field, say the reals, you may have a conic without any point, right? So this is a non-trivial form of P1, of the projective line. We prove using this kind of stuff that these 2 varieties, this 4-fold and this 5-fold, they don't have non-trivial forms. So they're always linear sections, actually over any field of characteristic 0. I have to say, of course, that in characteristic P, this is way too complex. I mean, we don't know a lot, actually, because the additive structures are more complicated, right? The nilpotent derivations, everything go crazy in characteristic P. So I won't say anything about that case. OK, so let me give you some glimpse on the ingredients. So this is very nice because it's actually very, very classical. It goes back to considering some linear projections that were actually considered by Todd in the 30s. So it's a very old thing that we revisited for this work. And it goes as follows. So pick the Grassmannian, 6 dimensions. So let's be concrete, lines in P4. So you have lines, OK? And you can define the so-called Schubert varieties, which are the following. take a point in P4. So this is Todd, by the way. It's a very nice paper by Todd. So take a point, P0, a line, then a plane, then a volume. Sorry, my drawing is not very good. Well, you can imagine. A P3, okay. And then you can define some sub-variety of the Grassmannian, the Schubert varieties. It's given by some very precise relation, incidence relation. Please don't read that. Don't read that. The main examples are the following. So inside the Grassmannian of lines in P4, remember please, you have the following linear subspaces. So you pick a plane in P4, a plane. So you can think over here, right? Lines inside this plane. So this is just P2 dual, right? So lines inside this plane. So this defines actually a P2 inside the Grassmannian. Another way to produce linear subspaces are, let's say the last one is this volume. You pick a point in P4. Say we're in P4. Pick a point, P0, I don't know. And take the orthogonal hyperplane if you want. And each point of the hyperplane, defines a line, so a point in the Grassmannian. So there is a correspondence between each point defines a P3 inside the Grassmannian. Which P3? Well, each of these points of this P0 orthogonal. Okay? And you can actually describe the Hilbert scheme of these guys. So if you look at all these guys, all the volumes inside the Grassmannian, this is, of course, the same as hyperplanes in P4, right? You pick a point, the hyperplane, and then that's it. So this is actually P4 dual, which is, P4 if you want. So it's a very explicit and very classical description of linear subspaces of inside this Grassmannian. This was done by Todd. It's a very nice article, I have to say. Also, there is a very nice description of the automorphism group of these varieties, of these quintic-Delpezzo varieties. As I already told you that this one, you can describe it. This is PGL2. This one, the automorphism group is PGL5. And there are explicit description of these guys as well. And moreover, you can describe the action on the Hilbert scheme. You can see whether it's transitive or not. This is very explicit because it's essentially, complicated linear algebra, but it's still very explicit. And so the main strategy following Fujita, by the way, is using linear projection, but in an equivariant way. So to do so, we need a very nice result, a very nice lemma, which is the classical. It tells you the following in the MMP version, if you want. If you have a fibration, a proper morphism with connected fibers, we already saw that this condition on the push forward is essentially having connected fibers. And if you have an algebraic group, a nice algebraic group connected, linear, say, acting on X, then there is a unique induced action on the base, Y. So this is very nice. You can transport action of algebraic groups from the source to the target. The problem is that we need slightly more. We need a dense open orbit. And this is not always the case. We cannot always have a dense open orbit downstairs. So we had to prove that. The third case is true, but we proved that in the additive case is also true. So you can, so if you have any proper morphism with connected fibers, say between normal, say projective varieties, if you want, then you can push your additive instructions to the base. So this is very nice because, to summarize, you can run the MMP with an open orbit. This is very nice, and as in the toric case, this works for the additive case. And actually, I have to say, this also induces a an additive structure on the generic fiber. So you can also say that the generic fiber is also an additive variety. So you have a lot of information, actually. Okay. So, okay, let's put all these things together and prove the theorem. I mean, I will give you a brief sketch of the proof. So it's the following. Start with your 6-dimensional Grassmannian, and let's try to cook up an additive structure. So the main strategy is the following. So pick a P3 like this. I'll erase it. Okay, let me just write it. Let me just write that a point induces this 3 sigma 3 0 P0. Anyway, it's just notation. Induces a P3 inside the Grassmannian. So pick this one of these volumes and do the linear projection. You go onto P5, but this is not surjective, actually. The image is a smooth quadric, 4-dimensional smooth quadric in P5. So you have a 6-dimensional variety. I have a rational map onto a 4-dimensional one. So, well, of course, we have to blow up the center of the projection, and you get a diagram like this. And here we can, once again, everything is really explicit. We can use, this is a classical result on these kind of things, that for the quadric, there is always smooth quadrics are always additive and in a unique way. This is a classical result, at this point, by Sharoiko. And what we proved actually was the following. This was some sort of new thing. We proved that this blow up is actually a P2 bundle over this smooth quadric. It's actually the projectivization of a rank 3 vector bundle, which is very precise. Won't enter into the detail, but it's essentially the spinor bundle, which was defined by Ottaviani, plus the trivial line bundle. So essentially, everything is really explicit. And since it's canonical, there are no elections. Every quadric carries 1 or 2 spinor bundles. Everything is canonical. So there is a canonical J4 linearization upstairs. And we can, once again, by hand, produce an action which, a J6 structure. So you have a J4 essentially, so 4-dimensional algebraic group, and you have to cook up some vertical J2 somehow. And this is done by, explicitly looking at some sections. Everything is very explicit because you have a very geometric description of G twiddle. Okay, that's the main idea of the existence. In a few minutes, I will tell you another way to do it, but this way is somehow better because it behaves well for fields different from the complex numbers. And then once you produce a J6 structure on G twiddle, you can push it to G by this Blanchard lemma. So that's the key point. Once you have a nice action upstairs, you can push it downstairs. That's the whole point of the construction. So let me give you, let me once again argue a little bit why this is unique. So as I told you, the Grassmannian the Hilbert scheme of these volumes inside the Grassmannian is a P4. And the action of the automorphism group of the Grassmannian, PGL5, is actually transitive on this P4. You can check it on coordinates. And by Borel fixed point theorem, you can always pick an invariant point in this Hilbert scheme. So you have a volume which is invariant, fixed by this action. You can do the whole construction that I just told you in an equivariant way. So you have let me just recall you here. What was the construction? You have the Grassmannian, you have a projection onto the 4-dimensional quadric. Then you blow up the center of the projection, and then you give this P2 bundle, okay? And then you can do this in an equivariant way. Downstairs, as I already told you, the action is unique. So there are no choices. And G twiddle is very explicit. I won't tell you what it is, this vector bundle, but it's a canonically attached vector bundle to this quadratic. So you can actually prove that the action upstairs has to be unique. Okay, for this particular how to say BP that you picked for doing the whole construction, and since the action of the automorphism group is transitive, well, essentially any volume works. So that's a brief sketch of the proof. As I told you, actually you don't need to do all this thing to cook up an how to say an additive structure. The Grassmannian is an homogeneous space. So it's the quotient of a Lie group, GL5, by some parabolic subgroup. And you can actually construct in coordinates some additive structure by considering the unipotent radical of this parabolic group. So anyway, there is a Lie theoretic way to do it in coordinates. I mean, over the complex numbers, this is nice. But if you want to do it in an arbitrary field of a characteristic 0, then you have to be careful. So that's why we use this more geometric way. Okay, so now let me give you a very short description of the boundary divisor. As I told you, the main point is that we want to describe this not only we want to classify these pairs, right? Not only the variety, the underlying variety, but also the boundary divisor. And we can do it because if you take now a plane inside this Grassmannian, sigma 2, 2, anyway, this is just a name, a plane inside the Grassmannian, you do exactly the same game. You do a projection, but now you get onto P6. G25 is 6-dimensional, P6 as well. And now you have a variational map. So you have a variational map from the Grassmannian to P6. And you can check that there is a unique divisor in this linear system. And this is actually the boundary divisor. And you can follow the whole construction. And you can prove actually that if you blow up this center, this plane, and then you blow down to P6, you can describe in a very explicit way this blow up. So let me describe it for you. Inside P6, consider the following situation. This is very geometric, actually. Take P1 cross P2. So this is a product of projective space. You take the Segre embedding onto P5. This is onto P5. And this is the hyperplane, the boundary hyperplane of your action. So you have the projective space. Let me just draw an affine space, A6. Here you have your hyperplane, P6, P5. And inside this P5, you take this the image of this P1 times P2 via the Segre embedding, and you blow up. This is a trefoil. It's a trefoil of degree 3, actually. And this is equivariant. And which is very funny, is I told you that there are infinitely many structures on P6. There are an infinity of additive structures. This is actually the naive one, what I told you, pick a coordinate and use it to, just say x0 plus a1, x6, x5, then x0, I should put, anyway, x1 plus a1, x0, that one, and so on. The naive additive structure. Just pick a variable and use it to sum. Among all the all possible structures on P6, this is the one that you get. And for the linear sections, for W and Z, this is very nice as well. Let me just give you the answer. Essentially, it's just taking hyperplane section of this Archisav link. So you have instead of P6, you have P5 now. Instead of P4, you have, instead of P6, You have P4. And the blow-up center before was the degree 3 threefold, obtained as the image of P1 times P2. If you take a hyperplane section, you get F1. And if you take another hyperplane section, you have the twisted cubic. And this is the center of the blow-up, and everything is super explicit and equivariant. And moreover, they induce the naive additive structure on Pn. I have to say, just in maybe 10 seconds, that this is the whole point. I mean, the whole point of doing this is that you can carry on you can keep track of the Galois action of your field in this kind of diagrams. For instance, it's not very hard to prove that if you have this Hirsebruch surface, the blow-up of P2 and a point, all forms of this variety are trivial because it's essentially P2 and a point. So the point has to be Galois invariant, and therefore this point has to be defined over your field, and therefore F1 as well, and blah, blah, blah. So this is the whole point of doing this kind of circuits of links, is that you can keep track of the blow-up centers and show up that the centers are defined over your base field, and therefore all forms are trivial. And just very quickly give you a glimpse on the case of singular varieties. So for threefolds, there is a classification by Prokhorov of G del pezzo threefolds. And essentially, by this classification, we are left to analyze the case of threefold with nodes, 1, 2, or 3 nodes. In the case of 1 or 2 nodes, we can show that, we didn't show it. We can essentially invoke some result by Prokhorov and Petronel that tells you that a Q factorization, so it's a birational map of these varieties, are isomorphic to the projectivization of some vector bundle. And actually, this vector bundle is very, very explicit. This is very funny, so I have to write it. These are simple vector bundles on the variety. So the only endomorphisms are dilatations. And we proved also with, so it's a remark, we proved with Adrian and Takachi that if E is a simple vector bundle on a normal projective variety, then the projectivization is not additive. And all these vector bundles happen to be simple, so it's over. So we are only left to the case of 3 nodes. And actually, this is, there is also a variational map from the blow-up of P3 at 3 points. And this is very easy to see that this is additive, because you have an additive action with a whole hyperplane of fixed points, right, with this naive action. So you pick 3 points inside this hyperplane, and that's it. And for surfaces, essentially the existence was treated by Derenthal and Lurgan. So we only had to study the uniqueness. And to do so, we used some explicit projective models that were provided very recently by Cheltsov and Prokhorov. And that's the end. Thank you.
Thank you.